So Fuad Khoshnaw is senior lecturer at the School of Engineering and Sustainable Development at the De Montfort University in UK, and he's also the editor of the Corrosion Case Study Atlas, or what was the exact title of the
Correct.
Yeah. So it's like a summary of all different failure cases, because what you have known or learned in the last days is that we always forget about everything. So having this all summarized in a book makes it easy to like check for your specific situation if there could be a certain risk and what would happen and what has happened, right? So it's very good idea to collect all the case studies. So yeah, and then please go ahead. Thank you so much for giving this lecture. And hopefully we can, I don't know, you can say if we should interrupt you or if we wait with the questions in the end.
Okay, yeah. Thank you very much, Yolanda, for this invitation. I'm happy to be here for this invitation in this summer course, let's say. Yes, please feel free in whichever way you do like. So if you like to ask the questions while I'm talking, just feel free, or you can wait if you like to the end of that. So whichever way, I don't mind. Just interrupt me whenever you want. So the purpose of this presentation, it is just to go through some what we call it in the title, decoding corrosion and failure understanding. So why both corrosion and other failures? Because corrosion is not the unique, I mean, maybe not the individual cause for some of the failures. It can be somehow contributing other failures in a high rate or in a lower. So we try to somehow link between these causes and also some cases and what can be done for the solutions. So that's about the title. As Yolanda said, my name is Fuad Khoshnaw. Please feel free to call me Fuad. I have PhD in mechanical and manufacturing engineering. At the moment, I'm senior lecturer in the School of Engineering and Sustainable Development at De Montfort University, which is located in Leicester City in the UK. This is my email, so feel free to contact me if there is any further action we need to do after this presentation. Okay, so I don't know, maybe I say things that very easy for you, for some of you. So please forgive me for that. Or maybe we go a bit in deep details in some aspects that you are not familiar. So the purpose, as we said, we try to make some links between how corrosion be affected and how it can be solved. And this can belong to some metallurgical aspects, mechanical actions, or manufacturing processes. So that's the purpose. We try to bring some pieces from different backgrounds, let's say, or some different reasons why corrosion or other types of failure happen. So as outlines, I try to, in the beginning, to show why components fail in general. When we say components, can be industrial components, mechanical or electronics, or buildings, so industry building components. And then we try to, together, to think about what are other things needs to be known when we talk about corrosion, when we try to diagnose any type of corrosion. What do we need to know in different directions, as we said? Then after that, we go through different types of failure and what are the reasons behind this failure. Corrosion can be the main one, or can be the second main, can be the third main. Then how this failure consequences on cost, safety, environment, etc. And all these will be somehow, we try to link it with sustainable design and manufacturing. During the presentation, we try to see some case studies, as Yolanda said. That's from the book that I'm editing. I will put the details of the book at the end if someone wants to contribute in the 4th edition at the moment. We try to do. I try to make the presentation in 2 parts. So the first will be somehow covering the first 4 steps. And then we talk about a little about sustainable development and how that can be linked with corrosion and failure analysis. Okay, so why do components fail? Any idea why do components fail?
Yeah. Maybe you should come here and speak.
Okay, then. Okay. No.
Improper design. Yeah.
Material selection.
Yeah.
Very good. Yes.
Yeah. Operation conditions is mentioned here.
Yes. Very good. Yeah. All correct. Yeah, that's good. So what you said, all correct. In simple way, if you try to give a first step to know why components fail, in any application for any material, there is something called applied, and there is, on the other side, there is a strength of that material or that system, let's say. And this can be anything about applied, not necessarily only load, can be different things. The load, it doesn't mean mechanical force. It can be any other external action coming, including load or stress. So it can be applied load or stress, can be temperature, high or low. So it's not only about high temperature, low temperature also, sometimes when it is very low, causes some problems. I will give an example about this later. Environment, when it is aggressive environment with high concentration or radiation. So all these are somehow actions will be applied on the material. And this, when it is out of the limit that the material can resist, then that's one of the main reasons why the components fail. Of course, operational material selection, all coming through this as well, as we said. So, but on the other hand, there is a strength of that material. And when we say strength, it can be strength like a yield strength, fatigue strength, creep strength, etc. All these mechanical strengths. And also toughness. Toughness is a measurement for impact or for crack propagation in fatigue. Hardness, when the material is soft and is in contact with another material, then there is no enough strength of that. And then corrosion also. Corrosion has also some measurement, which material has high corrosion resistance. So to avoid here, which the failure can be prevented, can be avoided when this side, the left side, is smaller than the right side. Or if we go from the opposite side, when the strength of the material is higher, So all these become higher than what's applied. So why any material yielded means goes to permanent deformation, because the applied stress is higher than the yield strength of the material. If this has happened, if that's the case, then this material fail, not fracture, but yielded. That means the material goes to permanent deformation and will not go back to the original dimension or the original size, even after removing the load. And in some application like shafts, gears, most of the mechanical beams, this is a huge and a big mistake in design, as we said, in appropriate design, when the strength of the material is lower than the applied stress. So let's agree on that in the very simple way. Why components fail? Because the strength of that material that is used, any type of strength in general, is lower than the applied stress or the applied actions, let's say. Okay, now with this definition, the statement about why components fail, we can somehow say what are the types of failures and the causes behind. That's slowly we go in deep and deeper with the slides. So for those that are not very much familiar with some mechanical failures or tests, when we say fatigue, that means cyclic stress. So it is not static, it is cyclic. And cyclic, we mean the applied stress, the amount, the magnitude or direction, or both, changing with time. So sometimes in tension, sometimes in compression, with time changing. And the amount, the magnitude of the stress is also changing with time. If that's the case, then this component is subject to fatigue. But the question is whether it will be fail or not. We go back to the previous slide. Is the fatigue strength of the material is higher than the applied stress? If it is higher, then most likely not fail, or at least it will last as expected of this lifetime of the material. Creep or oxidation. Creep is another type of mechanical failure. When there is a stress, so stress means there is a mechanical force on it, with high temperature. And that's creep, but for oxidation, it doesn't need to be under stress. It can be just only temperature. And when we say high temperature, it is somehow related to the melting point of the material. So if the melting point of the material is, let's say, for example, for type of polymer is 250 degrees, then probably we can consider 100 degrees centigrade is high. But if the melting point of a material, for example, steel, is 1500 degrees centigrade, then even 300 is not high enough to cause creep. And in general, it is not a fixed term, but in general, if the applied temperature with stress is around 0.5, half of the melting point, then at that time we need to consider the creep failure. So if the material has a melting point, let's say 1000 degrees centigrade, then 400, 500 is high temperature. Corrosion fatigue, when there is a fatigue and corrosion, just to try to summarize the types of failure that can happen. So this is type of stress corrosion. So stress corrosion can be with static load, when the load or the stress is static for a long time. It doesn't change the magnitude and the value and the direction, or can be changed. If it is changing, as we said, that will be corrosion fatigue. But if it is not changing that often, then it will be stress corrosion cracking. So it is a combination between corrosion and stress. Sometimes creep and fatigue happen. So the material, the component, is under cyclic load, but at high temperature. So for example, turbines, exchange boilers, heat exchangers, all these, with the time, there is a pressure, and this pressure causes stress on the tubes, on the walls of the heat exchanger. And when it is going to not work, so for example, working in the morning, not working in the evening, and even during the working, this stress is going up and down, then that's also, we can call it is fatigue. And if it is at high temperature, as we mentioned, around half of the melting point, then creep also has an action on that. So what does that tell us? Tell us that most of the failures we see around us, there is no one single action. There are multi-actions going, can be fatigue with corrosion, and can be with yield, can be with, for example, and when we say corrosion, there are so many types of corrosion. We will come on that. But in general, if we look at that, there are three main, let's say, factors or reasons behind most of them, not all, but most of them, it's coming because of number one, stress, mechanical stress. Number two, temperature. So when there is temperature. And number three is environment, when it is wet environment or there is any chemical solutions over there. So these three reasons or three factors are the main one, the most frequent reasons for any failure. So if you look around in buildings, in mechanical components, mainly it's about the stress, because stress is everywhere. You can't see somewhere or something has no stress on it. Anything is under stress. The chair we are sitting on, the table, the data show, all these things are under stress at the moment. And these stresses, they are not fixed. It is going up and down with time, but it depends on the frequency. So the frequency may be every minute or every hour, every day, it depends. So for example, the room we are sitting in at the moment, we are sitting, so there is a stress on the floor, on the beams, but when we go out, then the stress will be released. And then other people coming in, it will be another cycle of stress. So number one is stress, humidity, chemical reaction, environment, all these also available and exist in so many cases. Maybe temperature is not always there. It is in some circumstances, temperature is active in causing failures. So stress, temperature, and environment, let's say. Okay. Any questions so far? Is everything clear?
Yeah.
Yeah. To know this, how we can diagnose any types of failure and to solve that, we need some information, some background. Not necessarily will be very deep, but these are somehow will be helpful to understand what type of failure it is. In some details, maybe not everyone is familiar, I don't know, but if it is, you can just pass on it if it looks like it is first time you see that, but I'm just saying that it will be helpful if you go back and try to make yourself familiar with these details. Will be helpful in the future for any research on corrosion that you might need to do. These things, so the things that are linked with corrosion or any type of failure, not necessarily corrosion. First thing, we need to understand the material, what type of material it is in different ways. The chemical composition of the material, the microstructure of the material, what are the heat treatments being done before or after post treatment, what's the surface treatment has been done for this, and is there any welding somehow in the component being done. Other things also can be linked with type of material. So for example, is it bonded or can be, say, in contact with other material? So it's all about the material. We need to have enough information about that material to understand what's going on if it is failed. So that's one about material. Another one, we need to know as one of the colleagues mentioned, the operational conditions of that component. So it is under stress, what type of stress, it is cyclic or static, or sometimes it is a residual stress. You see, there is no stress on it, but because of some previous manufacturing processes or heat treatments, there is enough amount of residual stress inside the material. And this causes big problems if it is not being released before going to the installed in the component in the industry. So always necessary to make sure that the material that's used, it is free from residual stresses. Also, it is important to know it is under tension or compression and what type of strain rate. Is it slow strain or sudden load, let's say, or impact? All these things, the material behaves in different way when it is under slow tension, let's say, or under impact tension. And the same thing with compression. So these details needs to be known, again, similar to the type of material. Then we know the third one is the environment. Chemical composition of the environment, not of the material, the temperature, pH, if there is a liquid going, what's the flow rate of it? Is there any radiation? Anything about the environment. So this is like a puzzle. We need to put these together to understand what is going on, to diagnose and to avoid any similar. When we connect these things, what type of material, operations, environment, then that will give us a first hint what's going on. Maybe we still need more investigation in the lab, but in theory, when this data are available, then we can at least direct ourselves to which lab tests we need to go. So this is about the requirement we needed to know. I'm trying in the next few slides to focus on some of these material stress in more details. So what do you mean by microstructure, for example? How microstructure affect to, if you understand the microstructure that's coming from the manufacturing or from heat treatments or from welding, for example. So I assume most of you are familiar with this diagram, which is Fe carbon diagram, which is steel. This is the first step of understanding heat treatments and phase transformation of materials. So I'm not going in deep with that, but what I mean, why I wanted to show this, how is the microstructure and the chemical compositions can be linked together. This is just a simple example, and there are so many other examples can be. So as you know, steel is pearlite at room temperature, pearlite, which is ferrite and cementite. So this area is pearlite. I'm talking about steel, and in steel in this area, which is below eutectoid. The chemical compositions, how the chemical composition change the microstructure. If you change that, if you change steel to stainless steel, how this can happen and what's going on in the phase diagram. Stainless steel, as we know, there are two major elements needs to be in the stainless steel alloys. First one is chromium. Chromium must be there, but also there is nickel that enhancing the, let's say, chromium oxide layer with the substrate. So chromium, nickel is somehow helping corrosion resistance. This is ferrite, this area, this small area. It has been a bit exaggerated, this space, to be clear. So ferrite is a solid solution of iron with carbon. Austenite also is a solid solution of iron with carbon, but as you see, austenite can dissolve carbon up to 2 or 2.1 carbon at this temperature. But ferrite can only dissolve carbon at 723, very small amount, which is 0.025 carbon. That's at high temperature. At the low temperature, at room temperature, let's say, it will be 0.0025. So very, very small amount. So we don't have that much solid solution. What do we have in steel? We have ferrite and pearlite. And these are two different, ferrite and cementite to make pearlite. So pearlite is the combination of ferrite and cementite. These are two different chemical composition. And this by itself is a galvanic corrosion because two different composition, two different microstructure, ferrite with cementite. So when we go to the grains, this is already not solid solution, so not homogeneous microstructure. Coming back to the chemical composition, if we add chromium to make stainless steel, if you add chromium to change this phase diagram to stainless steel, what's happened? Any idea? What causes chromium? Stabilize what? Stabilize austenite or stabilize ferrite?
Is this saying like Nikoman and Kralty-Tassimov?
So chromium.
I told it in the corrosion course. You forgot it. it's a ferrite, right? So nickel is
Correct.
austenite
Yes.
fertilizer and chromium ferrite.
Very good.
Yeah, so it means that it changes the ferrite into austenite, right?
No, not the
If
chromium.
you,
No,
Only
nickel stabilized austenite. The chromium
Yes.
stabilized ferrite.
Ferrite.
that's correct.
Oh,
That's correct. So let's imagine this one, this loop of alpha ferrite. If we add chromium, that's make this loop, gamma loop, smaller. So this gamma loop has become smaller, much smaller. And the whole, this one has become very large. This small triangle, let's say, has covered everything at room temperature, alpha. And this is with 10, 20, 30 chromium. From 20, these phases, sigma phases, appear, which are not welcome in corrosion. Because why again? Because this sigma is different than alpha as a microstructure. So again, the galvanic action is coming in that one. So that's how, so this is the phase diagram of iron and chromium. How is that? By adding chromium or equivalent. So it is not only chromium. There are other elements acting similar to chromium. We will see that now. And the same thing for nickel. If we add nickel to this alloy, any alloy here, and redraw the phase diagram, austenite will be predominant at that time if we add nickel. And if we add both of them, we add chromium and nickel, there is a diagram called Schiffler diagram that's chromium equivalent and nickel equivalent. So that's equivalent, including chromium, silicon, and niobium. But for nickel, it is nickel, carbon, and manganese. So they don't have similar effect, they have difference. So for example, let's say this one, I can read that better. 1 chromium is equivalent to 1.5 silicon, and it is equivalent to 0.5 niobium. So if you add 0.5 niobium, it acts similar to 1 chromium. So the weight of action can add. If you have both of them, then duplex stainless steel appear, which are ferrite and austenite. In between, so this is fully or ferrite when it is chromium is high. When nickel is high, austenite is the predominant, but in between, that's duplex stainless steel, 10%, 20%, 50%, and so on for each. Why we are saying that? Because when we have two different phases, austenite, ferrite, same as here, ferrite and cementite. So this cementite acting as cathode compared to ferrite. So there will be a galvanic action in every grain, and that somehow causes pitting, and at the end causes somehow general corrosion on steel. This is about micro, just an example to go a bit deeper with the microstructure and chemical composition. We do similar thing now about stress. How we do understand stress, and if we go one step deeper than the normal calculation or just the calculation we understand, we need to link between what is the equations we use in stress calculation or stress analysis, but how is that affect inside the material, considering the microstructure of the material. So very easy. One first thing, we have different types of stress: normal stress, or axial stress, where the force is perpendicular, means 90 degrees with the cross-sectional area. This is cross-sectional area, force over area. And this is bending. When we have bending, you see this, that's bent. This is the compression side, and this one is a tension side. So this layer has become longer than before, and this layer has become shorter than before bending. This equation, some maybe you are familiar with, some not. That's not our topic at the moment, but we just need to understand the stress, and that's coming from force in both sides. So there is an external force applied on this. So we need to make a stress analyzing in a micro scale, going inside the material. How is that? Because usually when, as a mechanical engineers, what we do, we say the applied stress, we consider it as flat. So something like that. We say force over area. Which area? This flat area, cross-sectional area, the perpendicular. But in reality, it is not like that. In reality, it is, we know this story. So atoms, unit cell for metals, then this unit cell repeated in 3 dimensions to make a grain or crystal. And this crystal will solidify during solidification in different directions. So this grain solidified in this direction, but this grain solidified in this direction. This one solidified in this direction. So these are, we need to consider them. These are, imagine the previous one, the previous slide. This is the force applied on this cross-sectional area. But this cross-sectional area has 2 faces, this face and this face. And the stress on this face, the stress, the normal stress, which is coming from this force, if we analyze it, that will be F cosine theta, and this will be F sine theta. But the main point I want to highlight it here, the forces here on this surface are not equal. It depends on the angle of atomic plane orientation. So this is something, if we go to in deep investigation, these can be with transmission electron microscope or any other advanced methods, we can find out what is the exact amount of stress that's on, what's the highest amount of the stress that's been applied. So considering these details in the analyzing stress on components help identifying the weakest points in the system. System means the component. So especially where there is stress concentration factor. So if this one is plain bar, if it is plain like that, so there is no discontinuity, then that's somehow it is acceptable to do this calculation. But if it is like that, so this one, that's big diameter, large diameter, small diameter, then we cannot go through any normal equations to calculate the applied stress here. There is something called KT, stress concentration factor, and there are, to find out what is the stress concentration factor, or what is the value of the KT, there are charts, so many charts for each load, for each type of component. Is it plate? Is it shaft? It is under loading of bending or torsion or axial. So for each of these, there is one chart. And the highest stress is in between here, between the small diameter with large diameter, this disconnection. And the applied stress here will be, for example, if we just for 1 minute, let's take an example. So what are the parameters we have? We have D and D. So these are D and D, these curves. So D and D over D here is 1.01, so almost same. The second one is 1.1, sorry, 1.1. And the third one is 1.5. So let's take the third one, easier. That means this D is 15 millimeter, for example, just an example. This one is 10. So D over D, 15 over 10 is 1.5. So we use this curve now. So that's one. Another one is R, this radius, this fillet radius, or chamfer, if you like. This is called fillet. The connection between small d and large d has an R radius. This is here. This radius over small d. So if we know the radius and we know that the diameter, we said it is 10, for example. So let's say this radius is 1 millimeter. 1 over 10, it is 0.1. If we wanted 2, it will be 0.2. Let's go with 0.2. So R over D is 0.2, and D over D is 1.5. So use this curve, and this is 0.2. Go up, up, not this one, not this one, this one. So the KT for this condition, for this details, is 1.5. 1.5. What does that mean? That means the stress at this point is 1.5 times larger than everywhere else. Larger than here. And of course here, because this is higher diameter than lower stress. But even 1.5 times larger than the smaller diameter. So that's something correlating between the structure of the component from outside, how it looks like. So if something like there is a discontinuity in any way, then KT needs or not needs must be considered in the calculation. And from inside the microstructure, these atomic plane orientations need to be considered to find out what is the highest stress can be there based on this orientation. Okay, so this is somehow we talked about the how is the microstructure and the shape of the component affect, and also how is the inside the atomic planes can be related to stress analysis. Coming to again with the stress, so I try to combine this unit cell, any of this unit cell, with the fatigue one, fatigue. So imagine we are talking, when we say the applied stress, we focus on one unit cell because the failure happens in very small area. When this area starts to fail through any pit or any crack, this failure will propagate. The crack will grow and leads to failure. So the first point of where is the weakest point and why it is the weakest point is the main step we need to find out to avoid failure at the end. So I try to make a contact between, to make a link between the microstructure, or especially the unit cell, considering this, with the fatigue. So as we said, fatigue is why I focus a lot about fatigue, because fatigue is everywhere, as we said. There is very rare, you look around and see there is a component under static load. Very rare to find this. Even after 1 year or 2 years, the load will be changing. Even the mountains and the atmospheric pressure, the stress on them will be changing. So fatigue is everywhere, but it depends what is the frequency. It is every second, every minute, etc. So to understand fatigue, which is what we said, it is cyclic stress, and this can be axial fatigue, or bending fatigue, or torsion fatigue. So there are different types of loading, and these different types of loading, cyclic. So the bending can be cyclic, the axial can be cyclic, torsion can be cyclic, any type. So in brief, that's the stress and strain diagram. In longitudinal or static load, that's how it works, or what's the shape, this typical yield stress and ultimate. But in fatigue, that's going back to zero many times, and even it is under, even the applied stress is under yield strength, but probably after some 1,000 or 100,000 cycles, the material will fail. Fatigue strength is around here. So it is usually, it is under yield strength. But there is another test how to find fatigue strength. It cannot be shown here, but it is under yield strength. And the shape of the fatigue, I think you are familiar with this one. There's initiation of crack, and then the fatigue is propagates. So this is beach marks, looks like a beach marks. So can sustain till here. It is still working. So it is the crack propagates until we got this area. So this has become air. It's disconnected now, 2 pieces. But still this one can hold the load. But suddenly, in 1 second, very fast, it's called fast fracture, it is separated. So this is why it needs from time to time to have a regular check about the crack length through any non-destructive ultrasonic to see where's the crack is and how many cycles left to fail. If we do have this calculation, what is the applied stress and what is the history of these crack length, we can somehow approximate to find out how much time left to fail at the end. This is you can see these waves clearly, that's for one of the flange being seen. This is fatigue participates in more than 90% of all failures. But the main question is, this 90% doesn't mean that fatigue is the number 1 reason, maybe number 3 or number 2. So it is with corrosion or at high temperature. So it might be corrosion is the main thing, or creep is the main thing. but also sometimes in many ways, fatigue is the main factor for failure. So coming back to this one, imagine this one, there is a force causes bending, and there is a rotation, so that's also torsion. So different types of loading going on. And as we said, these are all unit cells, grains. So each grain has a huge number of unit cells, and these unit cells are sitting in different orientation angles. So what's going on? Let's start with this one. If you apply load here, this one is this side, because it is bending, so one side is tension and this side is compression. The lower layer is compression, it will be shortened, and the higher layer is tension, so it will be longer layer during applied load. While this load is loading at the moment, this point is under tension. When it is rotating, so going to number 2, this unit cell was here, has become in number 2. In bending calculation, this is in the center of the cross section, the center. So all the unit cell along this line, the stress is 0. And when it becomes to the lower layer, number 3, the direction of the stress is changed from tension to compression. So this is the same unit cell from 1 has become down to become compression. Then going number 4 is become 0 and then coming back. So in one cycle, it's only one cycle. This unit cell has become from maximum tension to 0, maximum compression, 0, and will be repeated. So imagine if this is a motor, shaft of a motor, and this motor 3000 RPM, that means this unit cell repeated from or exposed to tension and compression 3,000 times, going up and down. This going and down, tension, compression, causes cracks, causes pits if it is high stress. So atoms in the unit cell subject to cyclic that is tensile, compressive, so many times, this causes the crack. Okay, so we understand now inside the material when the stress is going up on the material, if it is cyclic, how the atomic planes and the unit cell responds based on the orientation and also on the cyclic load. Okay, any questions so far?
Online? No? Okay, no, good.
Good, yeah. So creep, as we said, temperature is the main parameter for creep. But when we say temperature, we need, in parallel, we need to know what's the melting point of that material. Because 200 may be high for one material, but very low for other material. Depends on the melting point. So these creep can be with turbine blades, with chemical plants, anything where there is engine components, whatever engine it is. So there is most likely stress will be there, and this stress can be, the source of the stress can be a mechanical force or can be gas pressure, fluid pressure, it causes stress. Also, maybe there is a fluid inside, even at high temperature, this causes some corrosive environment. And as we said, most likely the stress will be cyclic. Very rare you find something always under the same. So this is one of the case studies about the book I mentioned in the beginning and Yolanda mentioned. So you see, it is cracking, but the cracks that's showing here is not fatigue crack. So with the fractography, if you do some fractography test with scanning electron microscope, that will give some details what type of causes has become. Is it temperature or only cyclic stress? Okay, so now coming to the main point about corrosion. Why did I mention these in previous slides? Because corrosion is not separated from these types of failure. It might be the first main reason for failure, but also there are other reasons behind with some contribution, maybe 30%, 40% with corrosion, such as fatigue or even high temperature. So I believe we are familiar with the types of corrosion. We don't go through each of them in detail. We select few of them to go a bit deep in, because others may be not very common, let's say. It's happening, but not that much common in industry. So general corrosion, that's there's no material has zero corrosion rate. Every material, even platinum and gold, corrodes in some rate, but very low. But it is always, there is a corrosion. With pitting, this pitting usually happens when there is a passive layer. So the layer is cracks, and the ions, whatever ions is, for example, chloride ions, attacking the surface and going inside to make the pit is larger inside, even if you don't see it on the surface. So mostly aluminum and stainless steel are with this oxide thin passive layers on the surface, but some ions can attack the surface and make cracks or scratch and allowing the other ions to go inside and making eroding or corrosion inside the material. Stress corrosion cracking, that's as the name says, it is stress and corrosion. And this can be static. At that time, we call it stress corrosion cracking, or can be cyclic, we corrosion fatigue. Intergranular corrosion, that's, we go in deep with that in the next slides. That's somehow correlating between microstructure, specific microstructure, when it is going through different heat treatments or welding at high temperature, causes some changes in the phase transformation and the microstructure. So it is not the same as received before. Change happen, and this change causes corrosion. Galvanic, very popular one when two materials in contact in wet environment. Embrittlement, some environments, some solutions causes embrittlement to some materials. So steel is one of them. Embrittlement can come from cold temperature, very cold, minus 50, 40, especially steel. That causes embrittlement, and that causes big problems in some applications. We talk about this later. And it comes from some, for example, hydrogen embrittlement or sulfur So any solution, for example, oil products, which includes this element, and there is a steel in that environment, so the embrittlement can be happen in this environment. Selective leaching, when two phases, one of them soft, another one hard. So for example, as we said in the beginning, one phase is ferrite and another one is cementite. So cementite is hard, ferrite is soft. And if it is flowing of fluid inside, then this causes the ferrite spots of grains eroding easier than the hard one. So this different rates of corrosion in the same component causes some big pits or large pits on the surface. Erosion, that's happened when there is a fast flow of fluids going inside in tubes, in cylinders, causes, so it is somehow mechanical action with chemical. Microbiological, that's induced corrosion when there is some bacteria, causes deterioration of some elements, so sulfide or, yeah, mainly sulfide that causes some, and at the end will increase the acidity of the solution and increase the corrosion rate. So we try in the next few slides to see each one in some more details to find out how we can avoid or what are the reasons behind. This is general corrosion, which mainly it's rust. So with prevention, painting, sacrificial corrosion or sacrificial anode, if we link another material with it, somehow will help. So it is still. What about this one? Is it corrosion, this one, or something else, you think?
Sorry, the bottom picture?
Yeah, the second one, this one, is that corrosion or it is type of steel, looks like this. So this type of steel, it looks like it is rusting, but it is called weathering steel. And this weathering steel, it looks like this. It has another name also. It's called corten, or in long name, it can say high strength low alloy steel. So it includes some elements such as manganese, copper, mainly copper, chromium, but low. So it is not going like high chromium or high nickel. It's about 1 or 2% of these elements. And this is causes helps to make a layer on the surface. Looks like rusting, but it is not. It is preventing corrosion of this. So there are many construction, although the appearance is not very desirable, but it is can be considered as a cheap solution to prevent corrosion in wet environments. And this one, the advantage of that, with time, this oxide layer that's happening, protecting even more and more with time, preventing against corrosion to happen. So we need to somehow making a big difference between the rust and some other type of steel alloys which are already against, or they have resistance for corrosion, but the appearance, it is somehow similar to this. So it is a natural oxide layer, brown one, but there are no cracks or flakes as it has been seen here. So it just looks like a bit smooth. It is a rough surface, but the comparing with this one, there are no flakes, so you can make this difference. This is some companies they use, or some countries, if they are, especially if it is outside the cities, because as we said, the appearance is not that much attractive, but it is cheap comparing with, for example, when you do cladding by stainless steel, because here you can see if it is stainless steel, then the chromium and nickel become much higher than this type of steel. But it lasts for long, and the reason is because with time, this protective layer becoming stronger and thicker, so it will be productive. Galvanic one. So this is when two materials, that's very clear, this one. This is, so in very principle concept, corrosion happens when we have anode and cathode. So that's not corroding, and this one is corroding. So this is the anode, and this one is the cathode, and the bolt itself. So this is galvanic corrosion, and this one, it is galvanic, but also general as well. And galvanic because the bolt are different. It looks like this one, the bolt is more corroding, so the material here is anode compared with this one is cathode. Temperature also has an effect. So if it is going to high temperature, that causes creep at that time, or oxidation if it is high. This is again from one of the cases in the book I mentioned. The more details of that case study can be seen in the book. So in very simple way, I'm sure you are all familiar with this, how to avoid galvanic. So this is EMF series for the elements. Usually what we want to do, we need, so in general, the one that's the elements in the top is anode, is cathode, sorry. And the one that's going down is anodic. To avoid galvanic, we need to choose the materials, two materials that are not far from each other. So because this delta E between these two, if the delta E, the voltage potential difference is high, then the force that pushing the electrons from anode to cathode will be high, and the corrosion rate will be high. But when the materials are close to each other in this diagram, then the potential difference will be low, and the corrosion rate might become low as well. So that's a very simple way to avoid galvanic corrosion, to avoid metals that are far from. So for example, if you have copper and we put magnesium, then this one will be very soon will be eroding, and that will be somehow used as a sacrificial corrosion, because this one is corroding very fast to protect copper, or let's say SN, for example. Something we need to consider in galvanic corrosion is the area effect. Area effect is important because, so for example, this one, the steel is anode, tin is cathode, as this one is showing. So tin is cathode, Fe is anode. Here, steel and zinc. Zinc is anode, so protecting steel. Zinc is anode to protect steel. So choosing metals close in EME EMF series, considering area, so which area needs to be considered, isolating dissimilar materials, so between the two materials, if there is any isolate like polymers, gasket, or using cathodic protection. All these are the methods will be helpful. So I want to ask, what do you think? Which one is better? Anode is large area to be, or cathode will be a large area? Which one is more preferable to avoid fast corrosion if we consider only area effect? And of course, we need to know why.
Think about like the screw. Do you want the screw to be more anodic or more cathodic in something?
Okay, so if you have two materials and we can change the area, which one we make the cathode large area is better, or to make the anode area large is better?
Someone online?
Maybe we should make the choice A is better than choice B.
So let's say this one A and this one B. So the first one or the second one?
So
I think
the second one is better.
Second one is better?
Yeah.
so.
Okay.
Yeah, I think the cathode should be a large area, while the anode should be the small area. The why is because always there is ionic transfer from the anode to the cathode. You were asking about why. That is what I think. So
Yeah.
if you have large area of the anode, there will be more ionic transfer, which may also cause more corrosion.
So here we say the anode should not be small, but I think the problem here is this misleading picture, because you want always to have the steel protected, right? So in the right picture.
No, ignore the right one. Ignore the right one. So
Yeah,
only
okay.
focus on this one. Yeah.
So we agree that the anode should not be small.
So anode should be large.
Yeah.
Oh, okay, then I'm wrong.
Okay. So to answer this, let's go back to this one. How to stop or how to reduce the corrosion in this simple cell? We can make the corrosion rate lower in two ways. Either so ions of cadmium going to nickel. So that's one step. So it should be a potential. It should be a force to push the cadmium ions or electrons to go to nickel. That's half of the step. The another half to happen, nickel needs to receive these electrons. If they can't receive it, then the corrosion will not happen. So that's why in simple concept, we said to corrosion to happen needs to have anode and cathode. None of them alone can cause corrosion. Even anode is alone cannot, because if you send electrons, the anode needs to wait until the cathode receives these electrons, and this receiving electrons is another half of the process. So these two electrons needs to go, and then this needs to be. So how to let's say make the process slow? Maybe it is difficult to make anode is not corroding. That's a bit difficult. But maybe there is a way to make the receiving electrons is not easy. So waiting for some time to receive these electrons. If that's happened, cathode is not able to receive electrons easily, then that's one of the steps of protection can be considered. So based on that, anodes sending electrons to here, everywhere on cathode. Also here, anode sending electrons to all these cathodes. So which one will be faster to receive these electrons? To receive these electrons, the cathode one, when it is high or large area, receiving these electrons very easy. So it say here, it say I'm large area, send me more electrons, more. I can accept. But here, when this anode sending electrons to this small cathode, it asks to be wait. I have no area to receive all these electrons. So less cathode is better for large anode because this one will be corroding slowly. Why is that? Because the cathode has no such ability to receive all the electrons from anode. Smaller cathode, higher anode is better than the opposite. Does that somehow make sense?
Yeah, I even heard sometimes they paint the cathode for that reason. So to reduce the area or to eliminate it.
Agree. Yes, yeah. Yes, painting is another method to avoid corrosion. But we said if it is as it is, without any painting or isolation. So we are talking about area effect. It's important. So this one is important to be not be far from each other. This is one step, and another step to avoid large cathode. And that's good step really, because usually not always, but usually cathode are more expensive than, so we need a smaller cathode to prevent.
I have a follow-up question.
Yes.
Sorry. So for the previous slides, how come on the diagram on the right you have steel? My bad. For the next slide. Yeah, you have cathode as a steel, and you have a zinc as anode, and that seems like to be a better option than having tin above the steel, where we have a pit in the inside of steel.
Well, it should be not, there should be no porosity or defects on the surface. Considering that the coating is, there are no defects, this will be correct. But when there is a pit happens, so this one will be another story. We are going to another step of investigation after the pits or cracks or scratch is happening on the surface.
Yeah, this is called anodic protection, and it's not a good idea when you have.
This one is anodic.
You do have that quite often indoors when you have like tinned things for indoor environment, or like silver coatings on something like steel. It's not a good idea if you get defects in it.
Yeah, the difference between these two is both of them at the moment. Well, the question is about both of them exposed to the same solution at the same time. But here it is not. So this one is protected by, so the steel is not exposed to the air. So there's this example cannot be applied on this when there is no cracks or defects on the zinc surface. Maybe this one is a bit confusing if we consider these two together. This is area effect, this one, but this is just for how one of them, it is both of them steel, but one of them acts as anode, another one acts as cathode. Maybe that's the way that needs to be presented.
So then you prefer zinc coating or you prefer tin coating? Like, and it depends on this environment. It's indoor, outdoor. Gotcha.
It depends on the environment. Depends on the environment. And so, for example, this one, the advantage of this, so this one is protecting steel very well. That's good. But the dangerous here, the risk here, if there is any scratch happens, then the steel, the whole steel, even in very small area, will be susceptible to air. So this will be completely anode, and small anode with big area of cathode, that causes very fast corrosion. So somehow, let's say this one is this one will be similar to after the crack happens, or the scratch will be similar to that. So anode is small, here is small, still small, but because the hole is small, but the cathode, so this small area sending electrons to all the surface. So it will very fast corroding of steel happens. But for this one, even if the scratch happens, then still this one is anode and the steel is not going to be corroding. So that's somehow protecting general corrosion. But this one, as I said, if there is good coating of tin, then that's better solution. But in case there is any crack or scratch happens, then the whole steel will be at risk. And this is due to this effect of anode and cathode area.
Yeah, so we have 8 more minutes. I'm just giving a warning here.
Oh, really? Okay, 8 more minutes.
Yeah.
Okay. Then I need to go fast, really. I spent some time in this. So pitting corrosion, that's very common test in general, to give a behavior of the material about corrosion. I assume you are familiar with this. So some materials are active, always active. Some of them active, then change to passive. Then another material in some other solutions will be active, passive, then transactive. This will give some indications about the resistance of the material. Intergranular corrosion, I need to go fast. This is something happens in some materials only. For example, austenitic stainless steel, especially 304, and in some aluminum alloys as well. So austenitic stainless steel, it is austenitic, so one phase, which is good, homogeneous microstructure. But when it is going through sensitization temperature, this is sensitization temperature, from 550 to 850, it depends from one reference to another. Then if the material passes through this range of temperature, chromium carbide precipitation happens. So this chromium carbide, as you see, chromium coming from inside the grains. So from the grains coming on the grain boundaries. So the chromium content inside the grains will be less than before, because it has been segregated here as chromium area. So some places will be depleted by chromium, some of them not. And this is also, as you said, causes one type of galvanic. So that somehow happens in the heat affected zone in welding area, because this is molten, so, and this is base material, but heat affected zone, it passes through this temperature, which is sensitization range, and this chromium carbide happens. So this is before, this is after on the grain boundaries. And because this, it is not as before, the chromium has been depleted, then when this one is exposed to any solution, then these areas will be more susceptible to pitting or general corrosion. So how to solve it? We can use low carbon or other types of austenitic stainless steel that has the elements. So for example, 321 has titanium, and this one has columbium. This has more affinity to combine with carbon more than chromium. So chromium will stay, and these elements will combine with carbon. So this is somehow protection or fast cooling. So don't give a time to make this precipitation happens. This is type of stress corrosion cracking. The main point we need to understand in stress corrosion cracking is some alloys in some solutions causes cracking. So not every material in every solution. So these materials exposed to stress corrosion cracking in these solutions. Of course, there should be a stress as well. So not only chemical solution. And these are some other types quickly. So erosion, selective leaching, we avoid exfoliation. You see that's mainly happens in aluminum alloys. Hydrogen embrittlement. This is when hydrogen, let's say, molecules combine together to make a gas, hydrogen gas, and this hydrogen gas will slowly becomes bigger and bigger, causes a pressure on the sides here and makes these big, large. This is about fatigue, so, but there's no time to, yeah. So that was the quiz I was prepared. You can look at it later. So for example, how do we understand this? Two dissimilar metallic alloys, two dissimilar. So it shows what does that mean. A mild steel plate and a larger piece of austenitic stainless steel were joined together in a lab joint using, so there is a welding, intergranular, remember. So this assembly was subject to an applied stress during the service in oil industry environment for 1 year, where it's encountered issues related to pitting and cracking. So this one has so many possibilities of corrosion and other types of failure. Two dissimilar, that means galvanic. Mild steel, a not larger piece of austenitic, so there's a area effect of galvanic. There's welding, and it is subject to stress. So all these, and it is in oil. So many things we need to think about it when something like this information comes to us. I think I need to stop here. So that's was last one. I had another part, but it seems no time for doing that. I was about to talk about Titanic.
Oh, yeah.
The main reason was embrittlement, because of the very low temperature, and the steel was not right selection for very low temperature. So the material has become very brittle, especially when it hits something. So there is impact load. impact load at very low temperature for steel. This is in brief. Yeah, and something else we need to remember, every one of us over the world paying $0.87 per day because of corrosion problems. So it's very needed to be avoided. And this is the book. If anyone, it's already with Yolanda, she might share it with you. If there is anyone has any case study about corrosion case studies, it is free. And at the end, when the book is published, you will get a copy of the book. And it is open for as many as possible of case studies you can submit. Very simple contribution. It is only 300 words. What is the corrosion? Why it's happened? What's the material? And 1-2 images of that corrosion. So it is not a research, it is just a case study. Thank you very much. Any questions, I'm happy to answer.